Okay, so there are several units that we're not going to get to on the AP test. Some of them are quick. Two of them are pretty quick and easy. The first one's even quicker and easier. So it involves things you know already a lot, particularly from chemistry. And you might think, I don't remember anything from chemistry, but you do. So I looked through all the progress check questions for this unit. And so this is not going to be tested, but I think you should have I'm going to give you a cursory knowledge of it. I really think it would have been an easy chapter. I think you would have done well on it as far as the test goes. So electric charge. Neutral objects have an equal number of protons and electrons, right? So this up here is representative, a picture where draw representative pluses and representative minuses. Sometimes they will draw nothing in that circle, means that it's neutral. Okay, sometimes they draw, like if it just has minuses, it would be a negative charge. If it has just pluses, it'd be a positive charge, and if it has nothing drawn, it's neutral. But this is showing all the charges. And the protons and neutrons are in the nucleus, right? So they don't move around, really. They stay in the nucleus. If you were to mess with the protons and neutrons, that's a nuclear reaction, which isn't even a chemical reaction. And we don't tend to do nuclear reactions on a daily basis. So charged objects have gained or lost electrons only, right? They have not gained or lost protons. The nucleus is not getting messed with. So when electric charge moves, it's always the electrons that move. The protons and neutrons do not move, but if electrons move away from an area, they can leave behind a net positive charge. And that would be like in chemistry when, say, an iron atom loses 2 electrons, it becomes a +2 charge, right? If a chlorine atom gains an electron, it becomes a chloride ion with a -1 charge, right? So it's just the electrons that move. And it says an electrical ground is a big electrical conductor that is big enough it can, well, actually, I'm going to stop here, and I'm going to draw something for you. Actually, I'll come back to the the ground part. I'm going to go to the next thing here. So conductivity, we have names, we kind of classify things. So it says electric charges, that is electrons, move easily through what we call conductors. Okay, so it's something that conducts, electricity is something where the electrons can move through it. And as we'll learn, that's what electricity is moving electrons. So electric charges, electrons, move easily through conductors. The outer shell electron or electrons are not held tightly to individual atoms, but instead move relatively freely about the substance. So you remember that those outer shell electrons were called valence electrons. And in chemistry, we had ionic bonds and covalent bonds. And something you may have talked about for like 20 minutes all year was metallic bonds. Okay, so how do metals bond to metals? Like, how do you make a wedding ring out of gold and silver and, I think there's a little bit of copper. Is that what it is in there? In white gold. So when this is how they bond. So this is drawn as if it's, just to make it simple, say it's some metal in group 1, like sodium or potassium or something. So here's an atom with its electron. It's one valence electron. Here's another atom with its valence electron. Here's one with its. This guy's has moved somewhere over here, something like that. But if you count up all here, these 4 belong to these 4, and these 4 electrons belong to those 4. And there's as many pluses as minuses. So the piece of metal is neutral, right? As many pluses as minuses. But here's the thing. The minuses, these valence electrons, are kind of shared amongst everybody. So the way metals stick to other metals and why you can, mix gold with silver and they just still all stick is because metals tend to do this across the board. They will bond with each other by being this big sea of electrons. They call it a sea of electrons. And then these atoms, which are they're not really ions, but if you see the electron separate from the atom, then this is a positively charged atom or a positive ion, and there's its valence electron. And that's how metals stick to metals, is all these atoms are kind of, if you think of their electrons as pulled off, they're positively charged, and they're all stuck to this big sea of electrons. It's kind of like having a bunch of styrofoam balls in a box, and you throw in like honey or molasses in the box, and everybody's just kind of stuck to the molasses, and the molasses is kind of stuck to everybody. And that's the way metals bond. And the big reason we're talking about that now is, suppose I were to put a big plus charge over here, okay, a big positive charge over here, then the electrons would be attracted to the left, and they would shift from being kind of everywhere to shift to the left. Not all of them would go over there, because if all of them went over here, this side would be super negative, right? And electrons don't want to go someplace where it's super negative, but they're going to shift. And this side's going to become more minus, and this side over here is going to lose electrons and become more plus, okay? And if I hook up a battery to this piece of metal, we can actually take the electrons and pump them around in a circle, okay? And as they go around in a circle, that's what electricity is, sorry. So these things are called conductors, okay? So things that conduct electricity well are called conductors. And let me go to, I guess I'll go to the camera here. So electrical wires, on the inside, what do they tend to be made of? What's a wire made of on the inside?
No, copper.
Often copper. It doesn't have to be copper, but some type of metal, right? So let me grab here. I've got some material.
Can it also be gold?
It could, yeah, any metal. All metals are pretty good conductors. Gold is actually not as good of a conductor as copper, but gold doesn't tarnish. That's what makes it so it's stick and expensive. Is it doesn't, the copper, will turn greenish, right, after a while, like the Statue of Liberty. So they take gold to the, the space station and stuff, not because it's a better conductor, but because it's not going to wear out. It also doesn't work hardened, which means, if you take a piece of metal like a paper clip and you bend it over and, oh snap, I just clicked the wrong button apparently. If you take a piece of metal and you bend it, a paper clip a million times, like it gets really hard and it breaks. Gold doesn't do that. So that's just a different thing. But I have these wires in here, and it's kind of hard to see a little bit. I don't know if you can see right in here, but there is, yeah, it's not going to work very well. But there's this green part, and then right inside there's this little copper piece coming out. Okay, so inside, although you can maybe see some, actually, oh man, come on, focus. There, you can see this copper over here. So there's copper coming out right at the end of this thing, and then it's folded under, and here's some of it out here. So wires are made of metal, but the outside is not made of metal. So why is the outside of a wire? Why do we coat them with something that's not made of metal?
So that we don't electrocute ourselves.
Something like that. So the electricity doesn't have a way to get out, right? So we make them out of things that do not conduct electricity well, which we call insulators. And you might have heard that term for houses, something that insulates, keeps stuff in. So you have insulation probably in the walls or ceiling of your house to keep the heat in, or the heat out in the summer, if you're running air conditioning. So those things are called insulators. And I'm going to switch back to the screen here. So conductors have electrons that are easy to move, or have some valence electrons that can move easily, and things that are insulators do not. Okay, insulators, electric charges do not move easily. Their electrons are held tightly to individual atoms, and so I could show you something like you can still see my screen here, I believe, right? If you remember there from chemistry class, you had shapes of stuff, okay? So you had this tetrahedron thing. And diamond is actually all carbon. This is going to be really hard to draw. Shoot, if I can get this going here. I think it's like this and like this and like this and like this. and then another carbon. So it's much easier if I get out the model. But if you look at diamond, each carbon atom in a chunk of diamond has 4 bonds, and carbon, being in group 4, wants 4 bonds. So the carbon is all happy and stuff in diamond. But the thing is that this carbon has all 4 of its valence electrons taken up in a covalent bond, right? And these guys have other bonds too. I'm not going to try to draw them. It just gets hard to draw. So the point is that the diamond does not have electrons that are free to move, because a perfect crystal of diamond would not, because each carbon atom has electrons that are taken up in bonds. Oh shoot, I gave this one a 5th bond. Sorry about that. Sorry, that one shouldn't have been there. But graphite, it turns out, has a different shape. Graphite looks like this and makes this hexagonal structure. And it keeps going. I'm not going to draw all of them, but there's C's here at every corner here. And it makes this hexagon structure. And each carbon does not have 4 bonds. Each carbon has 3 bonds. So each carbon atom has 3 of its 4 valence electrons taken up in covalent bonds, but it has 1 extra electron sitting around. And so this is graphite, if I didn't say that already. And graphite is like your pencil lead, right? It's not really lead. I don't even know why it's ever called lead. But this stuff, the graphite in a pencil, actually is a decent conductor of electricity. It's not metal at all, but it has an electron that's free to move around. So I could show you, that later, maybe sometime if we have time. But graphite is a pretty decent conductor of electricity. And there's no real hard line really between conductors and insulators. We just kind of say, good conductor, good insulator. We're kind of somewhere in between. We're not a great conductor. We're not a great insulator either, though. We're kind of in between. If your skin gets moist and salty with sweat or something like that, you become a better conductor. If you remember something from chemistry about, ionic solutions conducting electricity. So it's not like there's a line right between them. It's kind of a spectrum, okay, between, really good conductors to really good insulators. There are other things, and these are more exotic, but it's important in our world today. Semiconductors are used in computers particularly. They take some silicon mostly. There's a lot of silicon in sand, silicon dioxide, and they purify the silicon, and then they dump some other stuff from group 5 or group 3 of the periodic table, and they make things called transistors. And the transistors are super important because computers work off of zeros and ones, and the transistors, if you can see my hand here, like computers used to have these big old things in them called vacuum tubes, a little piece of glass that suck all the air out. And so computers took up like a whole room. And then we keep making things smaller and smaller and smaller, but the transistor was a huge invention for all electronics. And so we're just going to mention it here. Semiconductors are another thing, but they're kind of more man-made, if you will, and how they work we're not going to get into today. And you may have heard of something else called a superconductor. And it says superconductors have essentially no resistance to electric charge flowing through them. And so here is the deal. When electrons, so if I just pick one of these electrons here, suppose that this is hooked up and it's a circuit, and this electron is trying to make it through this piece of metal. Well, it's really 3-dimensional, right? And these atoms are not stationary because they have a temperature. So they're bouncing around, and this electron, as it goes through, can bounce into atoms and stuff. And so actually, as the electron moves, it's not a smooth motion. It actually goes more like ba-boink, 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 ba-boink around through the metal. And it actually, electricity, the electrons are actually moving pretty slowly. You'd be surprised how slow those electrons are moving through the wire. The flow begins at the speed of light when you hook it up. When you hook it up, they're all going to start moving, even though this one's like, in the middle. It's not going to take a long time for it to start moving. The electric, we can't get into too much, but anyway, point being they bounce through here. So imagine that this is like there's one electron. Just pretend there's only one, and all these are people in a classroom, okay? And everybody closes their eyes, and this person tries to walk through the people, okay? Well, if the people are stationary, they might bounce into a couple. What would happen if you tell all the people in the classroom to start walking around as well, close their eyes and run, and they would start bouncing into each other, right? And it'll be harder for this person to make it through because they're going to run into more people, because these people are like covering more, the people that they're trying to walk through are covering more ground. So it turns out that for a metal, if you raise its temperature, that's making these atoms bounce around faster, that it's harder for the electron to make it through. And we say the resistance of the metal goes up. It's harder for electricity to pass through the metal when it's hot because these atoms are bounced around. Okay? Its resistance to electricity goes up. And it becomes a little worse of a conductor and a little bit worse of a conductor. It's still a good conductor, but a little bit worse. Okay? But something we found out not that long ago, pretty cool and interesting, is this. If you get these atoms to go slower and slower and slower, then the electron has an easier and easier and easier time going through it. Okay? But something strange happens because of quantum mechanics. If you've probably never heard of this, but do you remember in chemistry class where we started drawing, like, here's the nucleus, and come on, switch. Remember how we drew energy levels, right, around the atom? First shell holds 2, next shell holds 8, and so forth. And we drew an energy level diagram, something like, let's see, something like, oh, I'm doing it the wrong way. Forget that. I need to go the other way. Okay, you probably didn't realize this, but this is increasing energy. The energy levels get closer together the higher the energy of the electron gets. Well, it turns out that atoms actually have energy levels for their speeds, which sounds crazy to you, but a little atom cannot be bouncing around at any old speed it wants to. So now instead of an electron, this is a whole like atom. It cannot bounce around at any old speed. But at regular temperatures, these energy levels are so close together because it's so hot that nobody can see the atom, like would never notice the atom jumping from one energy level to the next energy level because they're just so close together. But if you get it really super cold, you can see that the atom can only have certain energies, only certain kinetic energies, so only certain speeds. So here's an atom, okay? And along comes an electron, okay? And if the electron bumps into the atom, it could give it energy to knock it up to the next energy level. But if the atom is super, super cold, this electron doesn't have enough energy to bump the atom up to that next energy level because that amount of energy is just so much. So the electron can bounce into the atom, but it can't give it any energy. Okay? So normally when we have an atom way up here somewhere, an electron bumps into it and it raises its energy and the atom bounces around faster and it gets warmer. In this case, when the electron bumps into it, it does not speed it up. It can't, because it doesn't have enough energy to get that atom up to its next energy level. So the electron will pass through without giving any of its energy to the atom, and the metal doesn't heat up at all, but it also doesn't change its resistance at all. And the big deal here is none of the energy of the electricity gets lost to the warming up the wire. All of the energy of the electricity gets used to make whatever the electricity is trying to make happen. Okay, so those are called superconductors, and they're exotic, but they essentially have no resistance to electric charge flowing through them. But this can only happen currently. We've only got it to work at extremely cold temperatures. But the bullet trains in China, they have levitating trains. They have superconducting tracks. If you've heard of an MRI machine, they make really, really big electromagnets. And I am told that the wires of the electromagnets use so much electricity that if the wires were not cooled to superconductor temperatures, the wires would melt in like a few seconds. So MRI's machines have superconducting coils of wires. They've cooled them down super cold so that none of the electricity's energy goes into heating up those wires. So we can have huge currents flowing through it, and make an image of a person's brain or something to figure out what's going on inside there. So we can make new technologies with these superconductors. So these are exotic. The semiconductors are man-made. Superconductors are exotic, but you'll hear about them, and they're really important for new technologies. So conductors and insulators are the main things to worry about. So I'm going to try something here. I do not know how well it is going to work live on camera, but we're going to try something here. I've got a roll of tape, and I'm going to pull off a piece of tape. Oh, no. Fold it over on itself. Take another piece of tape. I probably should have made it longer, but this roll has it's a little bit low. And if I can you see the pieces of tape? Kind of. Okay. So I don't know how well this is going to work. Let's see. I'm taking them and pulling them off of my table here, and nothing happens. Rats. Okay. I'll try one other thing. Certain tape works well for this, and certain tape does not work so well. I'm going to take the two pieces of tape. I'm going to stick them on top of each other. And actually, maybe the darker background will be better. Much better, huh? And go like this. And if I bring them together, I'll bring it this way. It's not working all that great. Yeah, it worked a little bit. They're kind of sticking. And these are not the sticky side. These are the dry sides of tape. It's not like this. I'm not sticking the adhesive to each other. It's kind of dying kind of fast. But if you get a nice dry day, if I went outside probably, but it's not going to work. You could get them, you'll notice them really attracting. And if you can get them off the roll or off of a table really well, you can actually see them repel. So I don't know what I could pull them off of, but this wood probably isn't the best idea. What's that made out of? I don't know. Let's see. Oh, I totally picked the wrong side. Shoot. I'll try one more. I had a feeling it wasn't going to work. Not working. Okay. So I'm going to go back to this. I'm just going to skip this. But these are things you probably knew already. Something you didn't know is this. Neutral objects are attracted to a charged object. So when you rub a balloon on your hair, Vincent, can you mute yourself? There we go. Okay. So if you take a balloon and rub it on your hair, you will be able to attract other things. So you rub it on your hair and you can, attract somebody else's hair, right? Now, their hair is not charged, right? You rub the balloon on your hair. The balloon gets charged, your hair gets charged, but you can take that charged balloon and attract somebody else's hair. Their hair is not charged, their hair is neutral. And this is the way that it works. In conductors, electrons can move. So if it's like a piece of metal, and R is the distance, like for gravity, the distance between them. And I'm going to show you something like this. So here's an animation. We've got this object. It's a conductor. This is a piece of metal. It's sitting on something that's not metal. I'm going to bring over a charged object, okay? What are these electrons in here going to do if they can move, because this is a big conductor? They're going to shift over to the wrong way. They're going to shift over to that side, right? Now this is overdone. They wouldn't all shift over there. But now this distance between the charged object and the minuses, like the center of minus, kind of like a, center of mass, like a center of charge, the center of charge for the pluses, this plus, is closer to the minuses than this plus is to the center of these pluses, right? So which force is bigger, the attracting force? So just don't worry about this for a second. These minuses have a force towards this plus, and all of these pluses have a force away from that plus. So which force is bigger, the attracting force or the repelling force? Well, it works like gravity. The minuses are closer to this plus, so they get attracted to the left harder than the pluses get pushed to the right. And so you can attract neutral things because the electrons will move inside the neutral object such that the opposite charges are closer together than the like charges. The same thing would be true if this were a minus. If this were a minus, a big minus, the electrons would move over here to the right-hand side, and the minus and pluses would be closer together than the minuses and the minuses. So you can attract things that are neutral just by being charged. The AP test doesn't worry about that, but that can really confuse people in real life. I think one of the AP classes you guys saw me rub a balloon on my hair and then stick the balloon to the wall. The wall is not charged. The wall doesn't have a charge. It's neutral, but it works something like this. If I bring a charged object next to the wall may not be a conductor, but the electrons will still move, okay? When the charged object is near the electrons of, in this case, instead of these being a conductor and the electrons being able to move from like way over here to way over here, now we're looking on a microscopic scale, down on like the molecular level. Electrons in these electron clouds are going to shift, in this case, to the left to be closer to the plus charge. So the left-hand side of the atom or molecule will be more negative than the right-hand side, and these atoms or molecules will be polarized. If you remember polar molecules from chemistry, that a plus, had a different center of charge for the positive than the center of negative charge. Well, these atoms are being polarized by the charged object, not because of what they're made of. Okay, so that's called polarization. And so I'm going to go back to these camera here. And here's a few things they want you to know. Come on. Or would have wanted you to know. If you take a conductor, so pretend that's a metal sphere, and another conductor, and let's just say we give this one a +3. The unit of charge is called a coulomb, okay? But a coulomb is a big charge, so 3 nanocoulombs means 3 billionths of a coulomb. And let's say this one is -2 nanocoulombs, okay? So this is a +3 charge and a -2 charge. What would happen if I touch them together, or what if I connect them with another conductor, like this is a wire? Is this one going to stay +3 and this one -2? If you take pieces of metal and connect them together, it turns out they won't, okay? So if they are, well, let's start actually easier. If I have 2 objects, and this one is a 4 nanocoulomb charge, and this one is 0, it's not charged at all, and I touch them together, they're going to share the charge, okay? So after they touch, this one and this one will have the same charge, and what charge will they have? Well, they want you to know electric charge is another thing that always, we believe, gets conserved. You don't make, if you make a new plus in the world, which is exotic and unique, but you can make a new plus, but you always make a new minus at the same time. So the amount of the charge of the universe is constant. Charge gets conserved. So these have to have the same charge. So they have to have a +4. We add these together, +4 nanocoulombs. But if we touch them together and they're identical in size and everything, if these are identical spheres, they will share the charge equally, right? Okay, so if these guys are identical spheres and you touch them together with a wire, they will share the charge equally. So what's the charge of each? Well, if we add these together, 3 nanocoulombs plus a negative 2 nanocoulombs, we get a 1 nanocoulomb net charge, but they have to, it's a plus 1, sorry. So they need to share equally. So this one's going to be half a nanocoulomb, and this one is half a nanocoulomb. Okay? What would happen if you take a big old one that is 3 nanocoulombs and you touch it to another identical one? That doesn't look very identical, but they would each get half. But what if I take this guy that's 3 nanocoulombs and touch it to something much smaller? Are they going to share equally? So, I'm sorry, suppose this one's neutral. They are not going to share equally. This one will get, like, if, you know, this one had a lot of plus charge, this one might gain, like, you know, a little bit of plus charge. Okay? So what would happen if I take this plus charge and touch it to something bigger than it? What if I touch it to something really big, like super big? Like, what if I touch this little plus charge to the entire Earth? Okay? The Earth is so much bigger than this plus charge that when they share the charges, they will not share them equally, and the Earth will gain basically all of the plus charge. Okay? And this will become neutral. All right? And you might say, but pluses don't move. You're right. Pluses don't move. Electrons will move from the Earth in and neutralize the charged object, and these are pluses and minuses, and now this is neutral, and the Earth will gain a little, has lost some electrons, but the Earth is so big, nobody's going to notice it lost some electrons. So this wire is called a grounding wire. Okay, and I'm not going to get all into it right now, but in the wall, you know, you have the plugs like this. This wire right here kind of acts like that. It's called a grounding wire, all right? It's a safety device. That's why some things have it and some things don't. But for right now, touching something to ground basically means remove all of its charge, okay? Because it touches the Earth. If this thing were a minus and it touches to the Earth with a conductor, then all the minuses are going to leave basically when it shares charge. These are not identical. This is so much bigger. It takes essentially all of the charge, okay? And I'm going to go back to this. I'm going to fly through this. You don't really need to know exactly this. But usually when you charge something, you started with interacting two things. You rub them together. They have to be made of different materials. One of them needs to like electrons more than the other, kind of like in chemistry when you had electronegativity. Some atoms, it's similar. It's not the same. But some atoms like electrons more, we said. They're more electronegative, and the bond between a highly electronegative and a not so electronegative atom will not be, they won't share the electrons equally. It'll be a polarized bond. Well, if you rub a balloon on your hair, balloons end up negative charge with hair. So the balloons, like the rubber of the balloon, likes electrons more than your hair. I don't know why exactly, just I know that's true. So you rub two things together. They often rub fur and, you know, on some plastic type of thing, okay? Then once you charge something, electrons could transfer between a charged object and a neutral conductor. The conductor ends up with the same charge as the charged object. That's kind of like what I was doing over here. You know, you had something that was plus and you're touching it to something that's neutral and it ends up plus, okay? Just take a charged object, touch it to something else, and you could charge it. But there's another way to charge something, and it works like this. It's called charging by induction. You can charge something with the opposite charge as the charged object by doing this. Here's the object. Bring close a charged object. It doesn't have to be plus, but it's plus. Which way do these electrons move? Do they shift, I should say? Are they attracted or repelled by the plus charge? They're attracted, so they scoot over here, okay? Now, what if I were to attach a grounding wire to this side? And it actually doesn't matter where you attach the grounding wire, but that's much harder to explain. So we're just going to do the easy way and pretend we put the wire over here. This wire is now attached to the ground, but the electrons in the ground say, ooh, plus charge, right? And electrons are going to be get given to or taken from the ground, okay? So the ground will give or take electrons to or from the conductor. And I worked on this animation for a long time. Ready? Electrons in the ground go, ooh, in. Clap, 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 clap. Thank you, thank you. So now, is this conductor still neutral? See, it was neutral before, right? Is this conductor still neutral? It has,
No.
it's gained electrons, right? Electrons went in, right? So now, if you remove the wire, and this is important, if I remove the charged object, then the negatively charged sphere would be touching to a wire by a wire to the ground, and the minuses would just go straight back, okay? So you have to remove the ground and trap those electrons in them so they can't travel through the wire back away when you remove the charged object. Now this thing is negatively charged. It turns out that the negative charge will not stay, well, so on a conductor, the charge will spread out. So they're not drawing the pluses anymore, but the charge will go on the surface of the sphere, okay? None of it's in the middle. So if you like cut the sphere in half and you could take a cross section, it'll all be on the surface, on the very outside, okay? And then let's just repeat it of the same thing. I'm going to go to something else here. I'm going to go to the other one. This is also stuff you knew a lot. Can't see it. So an electrically charged object can have one of two possible types of charges, we believe, right? We figured out that there were two different types of charges. Seriously, Benjamin Franklin was one of those people who helped us, figure out things about the, I want me. Yeah. Can I pin me? Pin. There we go. He really was one of the, people that was a pioneer in electricity. And they figured out that there were two types of charges. And that the same type of charge repelled, and the same type of, there were two types of charges, 1 and 2, if you will, and 1 and 1 repelled and 2 and 2 repelled. And they actually had word names for them, okay? In fact, they figured out, a long time before that if you rub fur on amber, you get this weird thing happening. Nobody knew about static electricity. And the word for amber, that's like petrified wood sap, right? In I think it's Greek or Latin, was like electron. That's the word for amber in like Greek or Latin. So they basically called them amber charge and fur charge. Okay, that's what they called them. Instead of charge 1 and charge 2, they called them amber charge and fur charge in a different language. But somebody figured out if you connect them, they can neutralize each other. So what types of things do you put together and make zero? What two types of things annihilate each other? Plus and minus, right? So they call them now plus and minus. Which one's plus and which one's minus? I don't know. Pick one. Okay? Do you want to pick this one as plus or this one as plus? It doesn't matter, right? Just pick one. So they're arbitrarily called plus and minus. There's no difference between plus and minus. Man came along and gave them names. We could have had them switched. I actually kind of wish they had. I wish electrons were positive and protons were negative, but they're not. They're the other way around. So on the atomic level, years, like 100 years later, when we figure out about protons and electrons, it's seriously like 100 years later, protons are plus because we already defined what plus was, and electrons are minus because we already said what minus was 100 years before we knew anything about them. Atoms with an equal number of protons and electrons are electrically neutral, and to charge an object, you can't really charge an object, you really have to separate charges. If things start neutral, you can't make a plus without making something else minus. You can't make something minus without making something else plus. So you must either remove electrons from something else and you become, if you remove electrons from, if the object gets electrons removed from it, it becomes plus or minus. If it gets electrons removed. Well, if it has an equal number of protons and electrons and it loses some electrons, it's plus. If it gains electrons, now it's minus, okay? Only nuclear reactions can change the number of protons, okay? I was surprised how much the AP test actually cared about this one thing. Electric charge is quantized, okay? Quantized means only certain quantities are allowed. Basically what that means is, what's the smallest amount of charge anything can have? Well, the smallest amount of charge is the charge of one electron or one proton, right? But their point is that they seriously have problems. And I was like, really, this is that important to you? But okay. They gave problems where it looked something like this. Here are two objects. This one is charged with a +2 electron charge. This one is charged with a +3 electron charge, and you connect them with a wire. These are conductors. Afterwards, what will it look like? Is this what will happen? This will be 2.5, and this will be 2.5. Well, if this is like a big charge, like 2 nanocoulombs and 3 nanocoulombs, you'll get 2.5 nanocoulombs and 2.5 nanocoulombs. But you can't have half an electron, right? There's no way that half an electron moved from, here over to here, right? To reduce this guy's charge and increase this guy's positive charge. That can't happen. So I'm not kidding. They've got a problem. It says in the progress check, it says, I've got 5 electrons, of charge, okay? And I touch it to 4 other objects. It's something like this. After I separate them, what are the options? And one of the correct answers is this, 0, 0, 5, and 0. Another one is 1, 1, 2, and 1 electron. And then another wrong, these are both correct. One of the wrong answers is 1, 1, 1, 1. Sorry, you can't see this. 1, 1, 1, 1 is not correct because this started with 5 electron charges and these only have 4 electrons worth of charge. And the other wrong answer was 1 1/4, 1 1/4, 1 1/4, 1 1/4, because you can't have a quarter of an electron. If this is 5 coulombs, like 5 nanocoulombs, and we'll see what coulombs are in a little bit, then that would work. But you can't have a quarter of an electron, okay? And they really seem to care about that. So I'll do just a tiny bit more. What is a coulomb? Well, in chemistry class, they talked about charges in terms of just number of electrons, like iron has a +2 charge, or the chlorine has a -1 charge, and chloride. So we're going to come up with what is that charge. So this is something different. Any charge equals the number of missing or extra electrons times the charge of 1 electron, right? But in real life, we don't measure things in electron charges because most of the time it's like, 500 million trillion electrons have gotten lost when you have static electricity. So the units we use are called coulombs. They're not made up of anything else like, they're not kilograms and seconds, or meters and seconds, or Kelvin. They're kind of a whole new unit. The charge of an electron, and this is on your equation sheet, is negative, of course, 1.60 times 10 to the -19 coulombs. What's the charge on a proton? Well, they have equal charges.
Is it the same but opposite?
Yeah, it's the same but plus, right? The plus and minus, again, are arbitrary, right? Man picked them 100 years before we knew anything about protons and electrons. Opposite charges, what do? Attract. Like charges, repel, okay? And so we could actually solve this problem if an object has a charge of 3.20 nanocoulombs. Has it gained or lost electrons, first of all? Well, it's got a plus charge, so it's lost electrons. How many? We could do a little conversion. If you can see my paper here, 3.20 nano means 10 to the -9, so we're just going to substitute it in. Nano means 10 to the -9, and convert from coulombs to electrons. 1 electron is a charge of 1.60 times 10 to the -19, and I can actually do this in my head. That's 2 times 10 to the 10th electrons got gained or lost. Well, it's a positive charge, so it lost 20 billion electrons. If its charge is way down here in 3.2 nanocoulombs, okay? So we measure things not in charges of electrons usually because it's just such a tiny amount of charge, but the AP test really wants you to know 2 things. Charge gets conserved. If it's 5 electrons worth of charge here, it's going to be 5 later. Unless it's an open system, unless something from the outside gives it, or takes away electrons, then it's an open system and, charge would not necessarily be conserved. But if it's a closed system, charge is conserved. Charge is always conserved. The charge of the system will be constant if it's a closed system, okay? And they do want you to realize that if you touch conductors together, they'll share the charge down as much as they can, but obviously not in quarters of electrons, okay? And I'm going to stop there. And we'll maybe have one more day on this at the most.